Hey everyone, welcome back to our look at matter. Last time we were discussing the phases of matter: solids, liquids, gases. We even talked a little bit about plasma. This time we're looking at how phases change. And here we have images from the Aurora Borealis Observatory of when the volcanoes out in Hawaii were being very active this summer. Now, what you see here is lava. Lava is, of course, liquid rock, very hot, very rapidly moving particles within that. And as it flows out and finds water here, there is a very violent natural uh, interaction going on, wherein the atoms, ions, and molecules within the lava, which are moving very rapidly, are encountering water, which is very capable of absorbing a lot of that kinetic energy. So the water is taking the kinetic energy away from the lava and undergoing a phase change to a gas, while the lava is cooling down and forming solid stone. And these sort of phase changes occur all over the place. And that's kind of what we're looking at today in this video. So phase changes obviously are kind of wild and crazy. And realistically, you can probably see that there's got to be something to do with temperature going on here. You probably have taken ice cream out of the freezer before and seen that in the temperature of the room, it starts to melt. While in the temperature of the freezer, it stays this lovely, tasty solid that we all enjoy. Same thing as we saw with the lava is hitting the water is going on with the ice cream interacting with your living room. Not as violent and incredible, but it's the same concept that there's something going on wherein temperature can cause a phase of matter to change into another phase. And really, that brings us back to our kinetic theory of matter. So, in the kinetic theory of matter, we're saying that matter is in constant motion. And that motion, you can't see it with your eyes, but things are just jiggling around. They're translating, they're vibrating. The whole universe is moving all the time, unless you're at absolute zero, in which case there is no motion. That's really the definition of that temperature. Absolute zero is the temperature where nothing's moving. So that motion that is has an energy associated with it. The energy of motion is kinetic energy. I will sometimes talk about this being more of a thermal energy, especially in the next video. But realistically, the particles are in motion. That's really what you want to focus on. Particles are constantly moving. The atoms aren't just sitting there rigid in space, not moving around. They are, in fact, vibrating into each other, colliding with one another, moving around each other all the time. And the faster that movement happens, the more violently that movement happens, the more kinetic energy an object has. And the more temperature, the higher the temperature is, because temperature is going to be a measurement of the average kinetic energy within a solid, liquid, gas, anything. Okay. And if you get enough of that kinetic energy going, if you're at a high enough temperature, a solid can phase change from a liquid solid to a liquid to a gas. Okay. So anything can change its phase given enough kinetic energy, given a high enough temperature. And that's a key concept. You may not be aware of temperature as a measurement of the average kinetic energy of a system. You're probably just aware that when we say it's 100 Fahrenheit, it's really hot outside. When we say it's 40 Fahrenheit, it's really cold outside. That's probably where you're at with an understanding of it. But really what we're saying is that when it's 100 Fahrenheit, the atoms, ions, and molecules in the air are moving much more rapidly. There's a lot more kinetic energy in the system than there is when it's 40 Fahrenheit. So phase changes occur all the time. I mean, you've gone into the freezer and made ice before, I'm sure. You've put water in an ice tray, you stick it in a freezer, you come back a couple hours later, and hey, you've made ice. If you took that same water and instead you put it on a stove and you were adding heat to it, then you would end up eventually causing it to boil. And the boiling water you see rising off of it, steam, of course. So ultimately, when I take away heat or I add heat, when I change the temperature that a group of matter is being exposed to, I will change its phase given enough of a change. Now, it's really important to understand that these changes are physical, they're not chemical. This is the first time we've come across this concept. A phase change leaves the matter intact. So, water, when you freeze it, is still water. It's a solid form of water we call ice. Okay, you could then melt it out and have a glass of water again. Like, you're not getting a changed substance when your ice melts into your glass of ice water. You're just getting more liquid water. Okay, it doesn't become some other chemical. That's a key concept. A chemical reaction changes what the chemicals are. So when two things interact in a chemical interaction, you're going to create new bonds between the atoms inside the matter. And those are going to be new chemicals that will exist. There's rules that we'll talk about when we get to that and how that all works. But for right now, just focus on this idea that ultimately, if I have ice or liquid water or steam, it's still H2O. It's two hydrogens bonded to an oxygen. I didn't change the molecule, it stayed the same. So, what's happening here is that heat energy, we're going to start calling it heat energy, which realistically is this energy coming from the motion of these particles. Okay, this heat energy is going to be either absorbed or it's going to be released during a phase change. So either I am slowing the molecules down and moving them closer together when I, for instance, put liquid water into my freezer, make an ice cube, or I'm having energy absorbed by it. I'm boiling the water, I'm adding heat to it, and I'm causing the molecules to speed up and expand and move much more rapidly. Now, that can come, when we talk about these, it really comes into two types of ideas. There's endothermic and there's exothermic, as either energy being absorbed or energy being released. An endothermic um, phase change here. The system's absorbing energy from the surroundings. The energy is going inside it. Okay, so whenever I see water evaporating, okay, it's taking energy in. I'm absorbing it. The water is boiling off. I'm putting more heat in and making it move faster and collide more frequently. And as a result, the energy is being absorbed from its surroundings. Okay. While in exothermic, energy is going out. So if I were freezing something, okay, if I'm going towards the solid side of the scale, then I am exothermic. My energy is leaving the system. I'm slowing down. I'm moving from a liquid to a solid or a gas to a liquid. All those types of movements are going to slow the system down, and ultimately those are called exothermic. We're going to deal with those exothermic and endothermic more later, but it's getting you used to this idea of this flow of energy, and these terms is very important, especially when we start building hot and cold packs together. So One thing about all these phase changes is they all come with different names. And I've put the common ones into a Quizlet for you folks, which you can find on my Schoology page. But ultimately, phase changes have a lot of language, and you probably know some of them. For instance, a solid melting to a liquid, or a liquid freezing to a solid. Those are really common. Liquids going to gases, vaporizing or vaporization, and gases coming down to a liquid would be a condensation. You've probably heard those terms before. Definitely the gas to a solid. Those are the most rare ones, I think. So a gas becoming a solid is deposition, while a solid becoming a gas is sublimation. And in those cases, the solid is going directly to the gas. It doesn't become a liquid in between. And those are pretty rare. You don't really just see that happening. Um, we'll see a little bit more of that in class when we fire up some dry ice. And dry ice, of course, goes from a solid to a gas. It's one of the cool things you might stick in a pumpkin on Halloween to give it some smoky effects, because the solid is going to immediately sublimate into a gas and come out the pumpkin. It looks really cool. And of course, there's recombination ionization for plasma. We don't really go too much into plasma, even though it's obviously a very abundant phase of matter. Now, all of these things exist on what's called a phase change diagram. The phase change diagrams, you're going to be doing one of these in a lab for me. But essentially, what you see in a phase change diagram is that the temperature will be going up, going up, going up, going up, going up over time. And then it comes to a point where the phase is actually changing. And when it comes to the actual phase changes, the temperature doesn't go up anymore, or down if you're cooling it off. The temperature actually levels off and stays the same while the phase is changing. So if you look at this diagram here, we have solid going up to its melting point, and then it sits at that melting point, and it stays there for a while. It stays there for a while, and it doesn't increase in temperature, but the particles begin to move apart. Okay, the phase goes from a solid to a liquid in this case, or a liquid to a solid. Either way, whether you're adding heat or taking it away. Now, once everything is phase change, once you have completely melted the ice or whatever solid you were looking at, it's now a liquid and can get heated up again. So now the temperature starts going up and up and up and up and up and up and up. Okay. And then you hit another point on the temperature where you hit the boiling point. Okay. I hit the boiling point and suddenly I stop increasing in temperature again. Okay, the particles start moving farther apart, much, much farther. Okay, actually, the vaporization one tends to be much longer than the melting one because the particles have to move much more further apart. If you look at the properties of solids, liquids, and gases, you'll see the gases are much different than liquids, while liquids and solids kind of have some things in common, much more so than the gases do, because you can compress the gas and all these sorts of things. They're much farther apart. So it takes a lot of energy to change from a liquid to a gas. And ultimately, it's going to stay at that same temperature until you hit the actual phase change completion, at which point you can then start increasing the temperature more and more and more. That's really about it for today. So next time we're going to be looking at thermal energy and heat a lot more, trying to really dig into temperature and understand some of the key terms there. I highly recommend that you take some time and look at Quizlet if you haven't yet. The Quizlet decks are going to contain a lot of the language from this particular video. If your notes don't have things like all these various definitions, and definitely the picture of this phase change diagram is going to be very important to you to have in your notes. Make sure that you're catching all the language and having that there, because that's going to be ultimately what I'm looking for in your writing as we go down. So when I'm asking you to do claim evidence reasoning on phases of matter, I want you to use the proper terminology, like vaporization and condensation, etc., etc. Okay, so make sure that you're capturing those either here or you're interacting with the Quizlet decks and learning those words so that you can incorporate them into your writing. Otherwise, you will not be doing as well as you could be. And that's about it for today. Have a great one, and I'll see you next time.